acids and bases. It's actually not too bad. Tastes quite good actually. It's quite intense. Okay, just give me a minute. Acids and bases. Now these are something that we come across in our lives all the time. Every day you're going to be interacting with acids and bases. In fact, within your own body there's all sorts of substances that have acidic and basic qualities. So let's have a quick look at what we've got here. So there's a whole range of substances and our pH scale runs from 0 to 14. Right bang in the middle is neutral, 7. Anything that is less than 7 is acidic, and anything that is more than 7 is alkaline. Now we're going to learn more about the pH scale in the next video, where you'll learn about it being a logarithmic scale, etc., and do all the calculations. But for now, let's just familiarize ourselves with acids and bases. So the most common substance on the planet with regards to life, water, is right bang in the middle. Thank goodness it's not a strong acid. It is a neutral substance. What I ate just now, a lemon, is right down the other end of the scale. It is a strong acid, pH of around about 2. In fact, you'll find quite a number of foodstuffs in the acidic side of things, like tomatoes, pH of 4, bananas, even with a pH of 5, fizzy drinks with a pH of 3. That's pretty strong acid. No wonder they're so bad for your teeth. And then here's one that caught me by surprise a little while back when I learned that actually milk is slightly acidic. I'd grown up thinking it was an alkali, but because of the lactic acid in it, it's actually about 6.5, slightly acidic. Now all of these things go down into our tummies, where they will experience the beast, the king of acids, our stomach acid, which is hydrochloric acid. Pretty potent stuff. If you could just get a little drop of that directly from where it comes out, put it onto the carpet, it's going to burn a hole in the carpet. It's nasty. Which is why when you throw up the things that you have been eating, it's not very pleasant at all. So lots of foodstuffs that you'll find, natural foodstuffs, on the acidic side of the scale. Now let's have a look at the other side. So sticking with bodily fluids, blood is actually very slightly alkaline, very slightly basic. And it has a pH of about 7.4, and that's monitored incredibly well by your bodily systems. In fact, it just keeps it with a very narrow margin, and doctors could use the pH of your blood to sometimes test whether you've got something particularly wrong with you. Saliva is another slightly acidic substance, slightly alkaline substance, but it ranges quite a lot, especially when you've had a lot of sugar. It can become pretty acidic. Then moving up the scale, let's have a see what else we got. We've got bicarb of soda used in cooking. That is moving slightly up the alkalinity scale or basic scale. Then soap, hand soap, on about 10. Ammonia solution at about 11. Bleach at about 12. Then we've got oven cleaner. It's really getting pretty potent now. Oven cleaner, strong stuff. You don't want to be washing your hands with that. It's about 13, and right at the top of the scale when it comes to pH is something like caustic soda, which we use for cleaning drains when they get all gunky and stuck with grease and hair and so on. You put that stuff down there and it just chows all the grease. So that's a very quick overview of some of the common acids and bases that we'd find everyday life. As you've probably already seen, the common ones, we might have a lot of foodstuffs on the right hand side, a lot of cleaning products on the left hand side. So foods are quite commonly acid in some way, and cleaning products are based on basic materials. So that's an overview of some of the common day-to-day acids and bases. Now, it's also important for you to understand and remember the common laboratory acids and bases. So I've just put them all up here for you. Your strong acids that you'll need to get to know: hydrochloric acid, sulfuric acid, nitric acid. Those are the 3 famous strong acids that you're going to come across. And then weak acids, there's acetic acid, which is ethanoic acid, or vinegar is where we commonly meet that one. Oxalic acid, which is used as a bleaching agent and cleaning as well. And carbonic acid, which we get in rain sometimes. So those are a few strong and weak acids. What about the bases? Bases, we've got the group 1 hydroxides. So sodium hydroxide, that's the one we most commonly use in the laboratory. but its very close cousin, potassium hydroxide, is also a very strong base. Lithium hydroxide, we don't come across it so often, but also being in that family, it is a strong base. And then there's a gazillion of weak bases, but like that one that we saw earlier, bicarbonate of soda, that is sodium bicarb, sodium carbonate, calcium carbonate, and ammonia, all of those weak bases. So get to know your strong and weak bases by heart. You just got to learn those things. So let's understand, well, what does it mean then, strong or weak? Basically what it means, if you've got a strong acid, like hydrochloric acid, if I were to take that molecule and put it into water, that molecule is going to separate into two. And you're going to get the H plus ion that we mentioned a little bit earlier, the hydronium ion, and a chloride ion separating away from each other. Now, if we did the same with a weak acid, like the ethanoic acid, the vinegar that we're talking about, you put that in water and it is also going to separate into an ethanoate ion and a hydronium ion. The difference is, as I've already put up there, is that a strong acid will do it almost completely. Almost 100% of the time it's going to get it right. Whereas a weak acid will only do it partially. Think of it like a sort of marine army being dropped on the beach somewhere to go and do combat. Now, the strong acid would be something like the US Marine Corps. You drop them on the beach, off they go, and they know exactly what they've got to do. The weak acid, well, that would be more like the Zimbabwean Marine Corps. Now, no offense, but Zimbabwe is a landlocked country. They don't have a Marine Corps. So if you drop them on a beach somewhere, they're going to say, hey, this is a beach. Let's play volleyball. Let's play soccer. Let's have a braai. Let's have a swim. And they're not really going to be that interested in the combat, although some of the enthusiastic ones may go and do that. So a strong acid knows exactly what it's doing every single time, whereas a weak acid will only do it partially. Now, what about bases? Same story, really. A strong base, let's take sodium hydroxide that we mentioned earlier. You put it into water, and almost 100% of the time, it is going to dissociate from each other in that manner. A weak base, like the carbonate, would only do it partially. So, strong versus weak is about how it behaves in the water. Now, just to pick up on a little detail that you may come across, you may have noticed that when I talked about the acid, we used the word ionize, ionization. Okay, but when we talk about a base, we talk about dissociation. But it's the same sort of process as the two parts separating away from each other. Why do we use a different term? Well, it's about the nature of that substance before we put it into the water. If you have a look at the sodium hydroxide, for instance, how is it bonded together? Well, sodium is an Na plus, an OH minus is an OH minus. It's an ionic bond. Therefore, being ionic, we don't have to ionize it. So all we have to do is disassociate it from each other. Whereas HCl is bonded covalently, and therefore we need to, as we pull it apart, turn them into ions, making it the term ionization. Okay, so that's strong versus weak, not to be confused with concentrated versus dilute. You see, concentrated and dilute indicate how much in moles of that acid or base there is per unit volume. It comes from the equation, C equals N over V. In other words, it's referring to the solution. Come back to our swimming pool water that I mentioned earlier. HCl is often used in keeping the chemical balance, the pH balance in this pool, right? Correct? So if I just poured in some HCl into a large swimming pool, I've put a strong acid into a large volume of water, therefore making it very dilute. Okay? So it's not dangerous. So it's referring, concentrated and dilute refers to the solution, whereas strong versus weak refers to the extent of ionization or dissociation in water, and that is referring to the substance. Okay? So concentrated and dilute, solution, strong versus weak, the substance. Okay, let's have a quick look now at the models of how we understand bases and acids. So the first dude who came up with a model was Arrhenius. In about 1887, he recognized that a lot of the acids produce that H plus ion that we were talking about, and a lot of bases produce an OH minus ion. So that was his little theory that he came up with, and it worked like a charm, except only in water. So there were limitations. What about if we wanted to use a different solvent? So two other scientists, Bronsted and Lowry, were racing for the finish line, and then eventually reached there at the same time, and as kind of competitors, their names got linked together in history about 30 years later, and they realized that if you just focus on that hydronium ion, the H+, then in fact you can think of acids as producing the H+, and bases as receiving the H+. Now, we call them proton donors and proton acceptors. You may be wondering, why are we talking about protons when we're talking about H+? Well, let's have a quick look at the structure of an atom. You've got your protons and neutrons in the middle, which is your nucleus, and then your electrons buzzing around the outside. Okay? Now, that's an H. If we were to make an H+, what we're doing is getting rid of the electron, which basically leaves us with just the proton, hence H+. Okay, so that's where proton comes from. So let's look at this in action. This can apply to any solvent, and therefore it's a much more usable model of acids and bases. So coming back to hydrochloric acid, our famous and favorite HCl, if we were to mix that with water, the HCl would donate a proton to the water molecule. Okay, so it's giving that H+ away to the water molecule, creating on the other side a chloride ion and a hydronium ion. Therefore, the HCl as a proton donor has acted as an acid. Okay, let's have a look at another example. If we took ammonia this time, which you know is a basic substance, instead of giving one of those H's to the water, it's actually going to receive one of the H's from the water, which makes it a base, a proton acceptor. So it becomes ammonium, and the water is left as OH-. So the ammonia acted as a base. Okay, you get the idea. So that's Bronsted-Lowry theory, which leads us to this whole thing of conjugate acid-base pairs. Conjugate from the word conjugare, it's a Latin word which means yoke together, like oxen pulling a cart. So we take our two substances and see, well, how are they connected? How are they yoked together? The conjugate base of an acid is the remainder of the original acid after the acid has donated a proton. So let's go back to our example, hydrochloric acid. HCl, remember, was the donor, gave away its H, therefore it is the acid. What is left behind afterwards was the Cl-, which makes the Cl- the conjugate base. Now, whilst we're on this example, we may have as well have a look at the fact that the water in this case was receiving that H+, therefore acting as a base, and the hydronium ion that it became was therefore the conjugate acid. So the acid goes with the conjugate base, and the base goes with the conjugate acid. Okay? One more example, just to get the idea. And this is now the other way around. A conjugate acid of a base, this is going to get really confusing, you're going to have to watch this again, is the ion or molecule that formed after the original base has accepted a proton. So let's take the ammonia example. See, remember the ammonia accepted a hydrogen from the water, therefore it was a base, meaning that the ammonium that it became is its conjugate acid. Okay? And water in this case, acting as an acid because it gives away the H+, and its conjugate base is the OH-. And that's how the whole thing works. Now, something to point out is that we've looked at just the passing on of one H+ each time. We can actually get this happening a number of times with polyprotic acids. So a monoprotic acid gives one H+, all right? Like HCl that we've been looking at, or in this case, nitric acid, it's got one H+ to give. But if it's got two, then we call it a diprotic acid, okay? Like H2SO4. And of course, if we have three, it's going to be called a triprotic acid, like phosphoric acid there. Now, here's an interesting thing, something you'll need to know, is the whole existence of ampholytes or amphiprotic substances. Now, these are substances that can act as either an acid or a base. The most famous one being water. But there are a number of other ones, and I want to give you a very nifty little method to be able to find out what those are. Okay, so pay attention. Here we go. This is a nice little picture. Let's take HCl as a starting point, just to illustrate what doesn't work. HCl If you consider those steps to be the process it has to go through to give off the H+, what's left behind afterwards was the conjugate base, which is Cl-. Okay? In other words, it gave away an H+, it was acting as an acid. Now, when it's at the bottom there, it's got no H's to give. So all it can do is to go back up the stairs and receive back that H+, which would make it a base, a proton acceptor. Now, in this case, it was acid or it was base. There was nothing in between. Now, let's have another look at a diprotic acid. So monoprotic didn't work. Let's look at H2SO4, nice common diprotic acid. Let's take him down the stairs. He's going to give away one of his H pluses, only one of them, leaving one of them behind, HSO4 minus. Okay, so acted as an acid in that case, came down the stairs. Now it's still got another H to give away. So once again, it can act as an acid, go down another set of metaphorical stairs to SO4 2 minus, that's the final conjugate base. Now when it gets down there, there's no more H's to give away, so all it can do is to go back up again. So now it's going to have to act as a base, go back up the stairs, receive back that H plus to get to HSO4. HSO4 now can go back up the stairs, back to H2SO4, receiving back at the original H. Now, can you see what's going on there? Okay, this little dude in the middle, HSO4 minus, was both an acid, or could act as both an acid and a base. Okay, now that is what an ampholite is. Now think of amphibians like a frog. Okay, a frog is an amphibian, can live on both land and water. Yeah. So there we go, let's make him a bit happier. There you go, there's a little frog. In fact, there's a funny little story about a song that's sung by Kermit's nephew, Robin, if you've ever watched The Muppets. And Robin sings this song, halfway down the stairs. And if you look right here, that's exactly what ampholytes are. They are halfway down the stairs. So how to identify ampholytes other than water is it's got to be a polyprotic acid that is halfway through the process of getting rid of its H pluses. Okay, so HSO4 minus is an ampholite in this case. Alrighty. And then the last thing to have a look at quickly is the different reactions that the acids can go through. I'll just quickly run through them with an example. You're probably fairly familiar with these. An acid plus a base will give you salt plus water. So for example, hydrochloric acid and sodium hydroxide. The salt is NaCl and the water. An acid plus a metal oxide also gives us salt plus water. So in this case, sulfuric acid plus magnesium oxide is going to give us magnesium sulfate plus water. An acid plus a metal carbonate also gives us the salt and water, but with carbon dioxide as well. So sulfuric acid plus calcium carbonate would give us calcium sulfate plus water plus the CO2 gas being given off. And then the last one to have a look at is acid plus metal gives us salt plus hydrogen gas. So that's just a little piece of metal put into the acid and it will give us hydrogen gas. So that about wraps it up. Those are the reactions that acids do. These are the introductory parts of acids and bases. Lots of content to study, lots of content to remember. We're going to get in the next video onto the calculations, which also can be quite tricky. But let's just quickly recap some of the things that we've been looking at today. So, number one, know your common acids and bases, particularly those laboratory ones that I was mentioning earlier. Number two, understand the terms strong versus weak, which applies to the substance, and concentrated versus dilute, which applies to the solution. Know the models of acids and bases, the Arrhenius model and Bronsted-Lowry. Be able to work out the conjugate acid-base pairs. Remember what an ampholite is and how to identify one halfway down the stairs. And learn the common acid-base reactions. And that's pretty much all you need to know from the introductory part of acids and bases. And do not test acids and bases by taste, because it can be fairly intense, pretty dangerous. In fact, you could die. So don't do that. It's not good, not good, not good at all. Unless you are a highly trained professional. It is time time. It is time. Do not try this at home.